Hello people! Keeping up with our tradition of building goofy stuff with Python, today we're going to see how we can make the flag of India using mathematics. To cook this recipe, we just need three things: a Python interpreter, or IDE of your preference. Google Colab is a great option if you like a plug-and-play environment. We need the NumPy library for creating the data. We would then use matplotlib to generate the plots and compile them into a video. Now that we know what we need, let us decide on our approach. We first generate the data for the x-axis using NumPy. Then, we split the matplotlib figure into three subplots. We plot sine, cosine, and tangent curves on the three subplots. We pick the colors appropriately, so that the pattern resembles the Indian flag. We also overlay the middle section of the cosine curve with an identical curve in blue, which would form the wheel at the center. To achieve a moving wave effect, we add a phase shift for each plot, and finally, we compile all the plots into a video using matplotlib. The code is split into three parts: setup, code, and driver. The setup part contains the library imports and configurations. We import the NumPy and matplotlib libraries. We also set the global parameters for matplotlib so that we can avoid the redundancy in setting the values. The code part has a class called animated charts. It contains the entire code. It has a method called run and the constructor. Of course, the code in the class is of no use unless it is instantiated. We instantiate the class in the driver part. We call the run method, which creates the plots and compiles the plots into a video. Let's dive into a deeper explanation of the code. The class animated charts has a constructor, which is the part that gets executed when the class is instantiated. It takes in the required parameters like working directory, frame rate, and the phase shift factor. The phase shift factor is used to achieve the moving wave effect. We then proceed to create the data for the x-axis. We split the data from 0 to 27 pi into 5000 equal spaces, using the linspace function of NumPy. I have chosen 27 pi, but it can be changed. The higher this value, the higher is the frequency of the wave. For mimicking the blue wheel in the middle, we take a copy of the middle section of the data. In the run method, we create a matplotlib figure with three subplots. To define a 1920 by 1080 resolution video, we set the dimensions of the figure to 19.2 by 10.8, with a DPI of 100. For each of the subplots, we perform some cosmetic changes, like removing the borders of the plots, establishing the y-axis labels, setting a transparent background for the subplots, etc. To achieve the end product, we would need four curves: an orange sine curve, a white cosine curve, a green tangent curve, and a blue curve identical to the white cosine curve. So, we initialize them accordingly. Since the tan curve can have infinite values at some places, we limit the values to 10 on both positive and negative sides. We achieve this using the clip function of NumPy. Digressing a little bit to demonstrate the function of clip. We can see that the values in the original array are capped at -50 and +50, as specified in the clip function. We decide on the number of frames. I have chosen an arbitrary number, but we can choose this value by multiplying the frame rate with the desired length of the video. It is worth mentioning that the higher the frame rate, the smoother the video. I have chosen a frame rate of 24. Once we have decided on the number of frames, we set up an animation routine, using FuncAnimation from matplotlib. We pass the figure, a helper function called animate, and the calculated number of frames. The number of frames decides the number of times of invocation of the helper function, animate. Let us look at what goes on inside the animate function. For each frame, we perform a phase shift on the sine, cosine, and tangent curves by adding a shift factor to the x-axis data. We calculate the values of the shifted data at every frame, and set the values to the objects of the appropriate curves. Line number 31 is not vital, but it adds a twist. This helps in adding an acceleration effect to the waves. This is how a sample plot would look like. Notice that the middle section of the cosine curve is superimposed by the blue curve. This is how the curve looks like if we fix the x-axis data between 0 and 27 pi. What would happen if we increase this to 108 pi? The crests and troughs of the wave become closely spaced. Feel free to experiment with different values, and comment down if you see any interesting effects. This is a sample of the animation achieved using this code. I have used a lower frame rate for the demo purposes, but if you want to have a look at the actual video, click on the card above. For more fun visualizations created using Python, head over to here. If you like what you see, subscribe and hit that bell icon. I'll meet you again soon with another fun and informative video. Until next time, happy learning!